Okay, folks, this is we're going to continue our discussion with about Alfred Wegener and his ideas on plate tectonics, and especially the idea of continental drift that he had talked about. And again, we looked at three different types of evidences that he used to prove his idea of continental drift. The first one was fossil clues. The second one was climate clues, and then the third one was rock clues, rock formation clues. The biggest problem that Wegener had, however, in this idea is that he couldn't explain how these sort of things happen, so nobody really took him seriously. He ends up dying in Greenland, and his ideas are forgotten for a little bit. So it took a political event, a big-time political event, for Wegener's ideas to start to become more widely accepted, and it took until about the 1950s. And it was because in the 1940s, Europe and most of the world was tackling this problem we call World War II. Okay, and a lot of technologies were developed during World War II, lots of different things that even we still use today. One of the greatest advances in warfare during World War II was the development of the radar. And so radar was obviously used to check enemy planes, but we also have this form of radar called sonar that was used in naval warfare, especially with submarines. So just to give you an idea of how radar works, because I think it'll help explain for sure what we're going to be dealing with here. This is the ocean, and on the ocean I'm going to put a boat. Okay, now this boat is a big destroyer. It has lots of midshipmen on it, and army supplies and things like that. So it is a boat traveling in the ocean. Submarines are basically another type of naval warfare that exists underneath the water, and submarines are able to attack boats that are on the surface of the water because they can't be seen. They're really hard to detect. You can't see through water, right? It's really dark, cloudy, and they're pretty far down. So a submarine is very dangerous to a boat on the surface. And so one of the ways a boat can detect a submarine is by using something we call sonar. So what a boat will do, or any ship, a destroyer, cruiser, anything like that, it will send out a pulse of basically sound. It's not sound, but we're going to pretend it's sound because I think it makes sense. They're going to send out a pulse of sound, and that pulse of sound is going to go back until it hits something. And once it hits something, it's going to bounce back and be received by the boat again. And based on how long it takes for it to get bounced back, you can kind of make an image of where things are. So this is great because if I'm sending out a signal and it hits something that's close to me, I'll be able to detect that, and I'll be saying, oh, there's a submarine in the water, and that will help my ship have a better chance of advancing and not being sunk, right? So it was a great way to protect ships against submarines. You could detect if a submarine was down there. Sometimes it might be a whale, but that's not the point. The fact that you could predict something was down there using this idea of sonar gave modern naval warfare a huge boost. Okay, so after World War II, however, once World War II was over, we didn't really need this technology for submarines, but scientists found it extremely interesting. I have these boats now equipped with sonar, and I can start mapping the ocean floor, right? If I shoot this down at the ocean floor, it should bounce back up. Well, what they found was that, contrary to popular belief, the ocean floor was not a flat surface. It was very rigid and bumpy. So you could easily detect this bumpiness using sonar, and it would kind of map out where ridges and things like that were. So the prevailing thought at the time was that the ocean was mostly flat, which turned out to be completely wrong. Okay? So again, this radar is important for naval warfare, and it showed that the bottom of the ocean was not flat, as originally thought. Okay? The bottom of the ocean is not flat like originally thought. So luckily, Google Earth does a great job of showing this and displaying this sort of idea. If I can get it to boot up. Okay, so if I zoom into Google Earth, I'm going to zoom in really, really quick. And hopefully you can kind of see here that the bottom of the ocean is indeed not flat. Okay, so it just zoomed us out. But the point is the bottom of the ocean is not flat. Okay? So this was an interesting thought. What scientists further found is that if you cross the ocean, there seems to be almost a lot of mountains right about in the middle of the Atlantic Ocean. We call this ridge of mountains. It's a volcanic mountain range. We call it the Mid-Atlantic Ridge. Okay, so not only is the ocean not flat, we also have a gigantic a gigantic line of volcanoes, literally right in the middle of the ocean. And you can see this gigantic line of volcanoes. If you follow the cursor here on Google Earth from space, you can see this gigantic line of ocean volcanoes. Okay, so we call that the Mid-Atlantic Ridge. So the ocean's not flat. We know this because of sonar, and actually what is in the ocean is lots of hills and mountains and things like that. And the middle of the ocean has a very particular line of volcanoes called the Mid-Atlantic Ridge. Okay, so once we had this idea, all of a sudden we're like, wait a second, this is why the continents are moving. This guy named Alfred Wegener was actually pretty right about this. Okay, that was that the seafloor is spreading, and it's because we have this hot magma coming up through the center of the ocean. So if you kind of think about it like this, I'm going to kind of draw what the ocean looks like. This is my volcano, and we have constant. Now, this is not an explosion volcano. It's a very soft, oozing volcano that just kind of shoots out magma all the time. Well, once this magma hits the water, it starts to solidify right away, and it'll turn into rock. And this solidifying does a couple things to the land. It'll start to push the land apart, right? So the more magma comes up, this ocean starts to get pushed apart and pushed apart and pushed apart until it starts to almost slide these continents apart from each other. So you think about how South America and Africa were once together. Well, of course they were, because at one point they were right on the boundary of this mid-ocean ridge. And they've just been slowly and slowly over millions of years, over these volcanoes erupting over and over again, these very soft oozing of volcanoes moving, these plates have been pushed apart and moved in opposite directions. So this idea we call seafloor spreading. That's when hot magma comes up and pushes crust apart. So the big key here is we want to know exactly. We can go down to the bottom of the ocean and see this, but at the time they couldn't really take a camera down there and look at it. So we have evidences now. So we're going to give some evidences of how we know that seafloor spreading is a fact. The first is age evidence. Okay, and no rocks on the ocean floor are older than 180 million years old. And I know that sounds like a really old time, but in geological terms, this isn't old at all. In fact, this is actually really, really new rock. Okay. Perhaps the best way to show you this is an image. Most rocks on Earth are approximately somewhere, I would say the oldest rocks on Earth are about 3 to 4 billion years old, and the rocks on the ocean are a fraction of that. 180 million years is not very much at all. So let's take a look at this picture right here. It does a great job of showing what we're talking about. Again, here's our magma being pushed up. Okay, going to push these plates apart. Well, what ends up happening is that if this ocean crust is being pushed apart, it's going to actually sink down underneath the continents. So when it sinks down, it melts back into the mantle, to this magma area, and becomes liquid again. And so the oldest rock then, the oldest rock on the ocean floor, it's the furthest away from the mid-ocean ridge, where this rock at the mid-ocean ridge is very, very new. Okay? So that's a huge bit of evidence that scientists were able to come up with. You take a sample of the age of the ocean rock, it's pretty young, really, really young compared to what is on the continents. So this cycle must be happening, this sort of conveyor belt of magma being pushed up and then back through. Okay? So age evidence, big part of it. Okay? Another, here we go, we should probably write down. Oh, there we go. Another type of evidence was magnetic clues. And this was a really defining idea. So in order to explain magnetic clues, I think we need to first understand what's happening with the Earth. If the Earth has the north, ooh, that's really bad, so we're just going to try to do that one over here. The Earth has a north pole and a south pole, right? Okay, so normally if you have a compass, we call that its polarity, and it'll be able to pick up where, oh my gosh, it'll be able to pick up which way is north, okay? Well, every so often, these poles are going to flip. And that doesn't mean north changes. North is still like Canada or whatever you want to say, but the magneticness of it changes. So it flips over. The south becomes the north, and the north becomes the south. And this happens periodically. I don't remember the exact amount of years that it happens, but it's a very periodic thing. So it'll happen very on a sort of a schedule. Okay? Well, in magma, there is this type of rock called iron. Okay? Or it might be magnetite. It's a rock that is attracted to this pole. And so when it's lava, when it's floating around in the lava, these particles of iron or whatever it is can point in a certain direction, okay, because they're liquid. They don't need to, they're not solidified, so they point in a certain direction. So they always point north. So they'll always point north. So as soon as the rock solidifies, it's hardened and it can't move anymore, and that northward pointing of the rock is frozen in time forever. Okay? Well, imagine if you have a seafloor that is constantly changing, right, where we have magma coming up at all the times. Well, most of the time, or all the time, the arrows will be pointed towards whatever way is north at the time. Okay? But we also know that these poles flip, remember? What if south is up top now? Okay? Well, these magma pieces are going to point down in this case. So over time, we have alternating bands of north and south polarity, which means that these rocks sometimes point north and they sometimes point south, which supports our idea that the poles of the Earth can flip. And it also supports the idea that these are moving slowly across, okay? These pairs, these are from the same set, right? Just like these are from the same set, and these are from the same set, okay? So in this case, north was up. In this case, north was down. In this case, north was up again. Okay, so these alternating magnetic clues show a good chunk of, or do a good job of showing how seafloor spreading is probably something that occurred. Okay, I want to show you one more image. And really quickly here. This will be a good. So as you can see here, I don't think I can touch it. As you can see here, the seafloor has different polarity. These white lines are reversed. That means it's flipped the other way around, and we have these alternating bands that are the same age. Okay, so polarity and age evidence show good signs of seafloor spreading. All right, that'll be it for today. Finish those questions, and I'll see you tomorrow.